Hello everyone, am I audible?
Yes, ma'am.
Okay.
Ma'am, I have one query.
Okay, please confirm whether my screen is also visible.
Yes, ma'am, visible.
Okay, okay, you can ask.
Ma'am, is this session and assignments are enough for exam?
Okay.
And sessions and assignments are enough for exams, NPTEL exams?
For exams, I am not sure. You have to go through the video lectures, right? If you have
Original video lectures.
video lectures, you should go through because I'm also not sure how the exams will be, like what will be the pattern. But definitely, these assignments and problem solving sessions will help.
Okay. And when will it be posted in some YouTube channel so that we can refer it later?
It will be posted. The link will be shared by the NPTEL team, so you can check the announcement in the course page.
Okay.
Let's wait for a couple of minutes. Let people join, and then we will start. Okay, I think we can start now. Others may join in the meantime. Good afternoon, all. Welcome to the second week interaction session for the course Semiconductor Device Modeling and Simulation. Let me introduce myself first. I am Ananya, a PhD student in the Department of Electrical Engineering, IIT Kanpur. I'll be your TA for this session, and couple of announcements before starting the session. In the last session also I have mentioned, but there may be some other students in this session, so I will tell these announcements again. So I am recording the session. It is mandatory to record the session. And also last time I used this Google Meet link for entire 2 hour duration for this live session. So there was no problem. But if there is any problem in this session, I will share another link, and please use that link in case there is any problem with this link. And please remind me maybe after 40-45 minutes if I forget to share the link. Okay, so let's start. Okay, so this is the first question. What is the ratio of FCC primitive unit cell volume to the volume of BCC unit cell? Assume that lattice constant is A for both BCC and FCC lattices. So this is for primitive unit cell, FCC and BCC. Again, for same as the last time, I will give a couple of minutes first. You should try yourself, and then I will explain the answer. And there may be different methods to get the final answer, so you should first try yourself, and then I will share the answer. Okay. Has anyone got the answer? Okay, I will start also solving here. Okay, you can solve with me. Okay, so for primitive unit cell, okay, for primitive unit cell, number of atoms in primitive cell is 1. Okay, in FCC, so number of atoms will be how many number of atoms will be there in FCC unit cell? So This was discussed in last class also, last session also. Okay. Can someone tell me the number?
Two, ma'am.
For FCC, lattice, so the lattice structure will be this face centered cubic, right?
Ma'am, 4 items per unit cell.
4 atoms. Okay. So 1, 2, and 8. Then its faces. There will be 6. So total 1 by 8 into 8 plus half into 6 equal to 4. Okay. For BCC, number of atoms will be, so for BCC there are 8 corner atoms.
2 atoms per unit cell.
2. Okay. There is one body center here. Okay. So for primitive FCC, for this cell the volume will be V equal to AQ, and for this also volume will be AQ. And for primitive unit cell, number of atoms will be 1. Okay. So to get the volume of primitive unit cell of FCC, we can do for primitive FCC, we will divide the volume by 4. Okay. For BCC, it will be AQ by 2. Okay. There are many methods to get this solution also. You can determine the primitive unit vectors for BCC, so that I will discuss in the next question also. So you can determine the primitive unit cell unit vectors for FCC and for BCC, and then also you can determine the volume. So I am using this method. This is a bit simplified. So you can now get the ratio of the volumes of primitive FCC and primitive BCC. So what will be the answer?
Half of unit.
Half. So answer is A. Okay. Is there any doubt in this question? I hope it's clear. Okay. So the answer is A. So let's go to the second question now. Let me see how many people have joined. Okay. Okay, so this is the second question. What is the volume of the primitive unit cell of reciprocal lattice of FCC direct lattice? So direct lattice is FCC. What is the reciprocal unit cell, and then what is the volume of primitive unit cell of that reciprocal lattice? Okay. The lattice constant for the direct lattice is 5 nanometer. So for the calculation, you can start with some lattice constant, say as a variable A, and then in the final answer you can put A equal to 5 nanometer to get these answers. Okay. So can someone tell me what will be the steps for this question? Okay. Let's first let's not consider this lattice constant. Let's consider only the FCC direct lattice part, and we will do the calculation. You can do along with me, and then in the final answer we will use this 5 nanometer lattice constant. Okay, so let's start. So what is given? It is a FCC direct lattice. I will do few more steps here. You can get with much less number of steps, but for clarification I will explain from the direct lattice, FCC direct lattice. So it is a FCC direct lattice. We will first determine the volume of the primitive unit cell for FCC. Okay, that the way we did the last example, and then primitive lattice vectors for FCC. What will be the volume of primitive unit cell for FCC? So let's first do the for the direct lattice. Okay. Okay. So this is an FCC lattice. Eight corner atoms. Okay. So number of atoms, as we have calculated in the last question, is equal to 4. Okay. So volume of and this lattice constant here, let's consider as A. Okay. Volume of okay. Let's look at it. Primitive unit cell will be A cube by 4. You can stop me if there is any confusion in between. Okay. Now, as I have mentioned, to get the volume of primitive unit cell, there are other methods also. So let's try that. First, for that, we will determine the primitive unit vectors of FCC direct lattice. Okay. So let's take these directions as X, Z, and this as Y. Okay. So the primitive unit vectors will be connect the nearest neighbor. Okay. the, these are the two vectors, and this is the third vector. Okay, so it will connect the next nearest two atoms. Okay, so let's, if this is A1, this is A2, and this is A3, suppose. So A1 will be this this whole distance is A. So for A1, in x direction, x component will be 0 because this is in this plane. Y will be A by 2 and Z will be A by 2. So the vector will be A by 2 y cap plus z cap. Okay. Similarly, you can write A2 and A3. Can you give me the answer here? What will be A2 and A3? So it will be A by 2 x cap plus z cap. Okay. That's y cap. So these are the primitive unit vectors, right? Now these primitive unit vectors will give us the volume of the primitive unit cell. So when we have 3 unit vectors, so the volume contained by the 3 unit vectors, how we get by as A1 dot A2 cross A3. Okay, that will give the volume of the primitive unit cell. So first let me calculate A2 cross A3 so that there is no calculation mistake. Square y cap z cap by 2 0 A by 2. This will be A by 2 0. So what will be the value here? X cap minus A square by 4, okay, minus y cap, okay, minus A square by 4 plus z cap A square by 4. Just solve this determinant. Okay, I hope you are following what I am doing. Like, at least give me yes, no or something in between, so that, because when I am in presentation mode I cannot go back and check whether there are people in the meeting or someone is actually listening or not. Okay.
Yes, ma'am.
Okay. So now what will be A1 dot this unit cell, this vector, so the volume will be, so this vector dot product of this vector, right? So this is plus A cube by 8 plus A cube by 8, so it will be A cube by 4. So we get the same answer. So this is for direct FCC lattice. Okay, I hope it is clear and you have also calculated along with me, right? Next, go to reciprocal lattice. So, okay, where is my cursor? Okay. For reciprocal lattice, lattice vectors will be B1. This is a vector. And for reciprocal lattice, how we calculate the lattice vectors? So that the formula is 2 pi A2 cross A3 by the volume of the direct lattice. Okay, so it is 2 pi. Volume of the direct lattice is primitive will be a cube by 4. So a cube by 4, and a2 cross a3 I have already calculated last time, right? This is so a square by 2, x cap is minus, I guess. Okay, a square by 4. This is 4 plus minus. Tell me if I do some calculation mistake here. Okay, so the final answer will be 2 pi by a minus x cap plus y cap plus z cap. Okay. Similarly, B2 will be 2 pi A3 cross E1 by volume. So that will be 2 pi into 4 by A cube. So let's do A3 cross A2. Yeah, A3 cross A1. Okay. What was A3? 8 by 2 0 a by 2 a by 2. This is correct, right? By 2. Let me check also. XY, XY and YZ. Okay. So this will be x cap a square by 4 minus y cap a square by 4 plus z cap a square by 4. Okay. So a square by 4 x cap minus y cap plus z cap. So B2 will be 2 pi by a x cap minus y cap plus z cap. Okay. B3 will be 2 pi A1 cross A2 by volume, and final answer will be if you do the final calculation. I'm just looking at these values, like here x is minus, here y is minus, so I'm writing you can do the calculation and you will also get the final answer as this one: 2 pi by a x cap plus y cap minus z cap. Okay, so we got the lattice vectors for the reciprocal lattice. So these are the lattice vectors of the reciprocal lattice, right? So now we can determine the volume. Okay, so let's calculate that. B1 is this. Okay, for volume we will calculate B1 dot V2 cross V3. So volume will be B1 dot cross B3. So let's first calculate B2 cross V3. Determinant x cap, y cap, z cap, and for B2 so let's take common a square 2 pi by 2 pi by a was common in both the in all the expressions, right? So let's take that as common. 2 pi by a, 1 minus 1 for B2 with y cap it was minus 1 and then 1, and for B3 another 2 pi by a and 1 minus 1. Okay, so 4 pi square by a square with x cap it will be 1 minus 1 0. Okay, minus y cap it will be minus 1 and minus 1 minus 2, and plus z cap it will be 2 plus 2. Okay, so it will be 8 pi square a square. Okay, y cap plus z cap. Okay, now our B1 was 2 pi by a. Just let me check. Okay, minus x cap plus y cap plus z cap. So the volume will be dot product of these two vectors, so that will be 2 into 2 pi by a. Okay, 2 pi by a into 8 pi square a square. Okay, so this is 32 pi cube by a cube. Okay. So now we got the volume of the primitive unit cell of the reciprocal lattice of FCC direct lattice. So this is in terms of lattice constant A, which is the lattice constant of the direct FCC lattice, right? In the question, it was given as 5 nanometer. So to get these answers, so final we got volume as 32 pi q by aq. So what will be the final answer? You can do the calculation and tell me what the answer is, A, B, C or D. And please check the unit. The unit is given as per centimeter cube. So 5 into 10 to the power minus 7 I am writing. Like nanometer I am converting as in terms of centimeter. So what is the final answer?
Option A.
Yeah, option A. I am also calculating, so give me a minute to. Yeah, option A is correct. So the answer is 7.993 I got in the calculation. Minus 21 per centimeter cube. Okay. So here you have observed that the volume is the unit is per centimeter cube, right? It's given as per centimeter cube, whereas for direct lattice volume will be in centimeter cube. Okay, so reciprocal lattice is like inverse of the direct lattice. Right? So everybody got the answer and steps are clear. Okay. Okay, I hope there is no confusion. So if any kind of lattice is given, even not FCC or BCC, any random lattice also, you can get the reciprocal lattice vectors and volume of the reciprocal lattice using these tips. Okay. So the answer is A. Okay, let's go to the third question. Okay, the answer already I have given. Let's go through the question. X-ray diffraction patterns are used for studying crystal structure of solids because what is the correct answer? They are energetic radiation which can penetrate through crystals. They are electromagnetic radiation and hence do not interact with crystal. This is obviously not true, right? If there is no interaction of X-ray wave with crystal, then we will not get any information from that. Their wavelengths are comparable to interatomic distances. Okay, so that is the correct answer. In crystals, what is the typical interatomic distance? Can someone tell?
Few angstroms
In
or
angstrom.
few nanometers.
Yeah, it is in angstrom. So for silicon it is 5.43 angstrom, right? So that is the lattice constant. Okay, nearest neighbors will be that will be root 3a by 4, so that will be the distance, but typically it is in angstrom. And also X-ray wavelength is comparable to that, and because of that diffraction happens. Okay, diffraction happens when the particle size is comparable to the wavelength of the electromagnetic radiation, and based on the diffraction pattern we get information about the lattice. Okay, so this is the correct answer. Correct answer is C. Okay, let's go to the next question. So this is question 4. This is again on reciprocal lattice. So most of the questions, reciprocal lattice will be FCC with FCC direct lattice, because the most commonly used materials, especially in semiconductor, so that is silicon, and silicon has FCC lattice structure. So that is why this question is given. Consider the reciprocal lattice of FCC direct lattice with a lattice constant A. What is the length of gamma 2x and x2l vectors and angle between them? Okay, so you can refer to the lecture notes and see if you can get the answer, because this was already covered. So I will wait for say 1 or 2 minutes and you can give me the answer. So in the lecture note, the gamma, x and l points are given. Here I have also given the reciprocal lattice of FCC lattice. This is gamma, x, and k here is actually l. So sometimes it is denoted as l and sometimes it's k. So this is the same point. So you can get the coordinates for these points and then calculate the distance between gamma to x and gamma to l and the angle between them. For angle between them, you can directly use these two vectors given as 1, 0, 0 and 1, 1, 1. Okay, those are the directions. So for gamma to x, this is 1, 0, 0, and for gamma to k or gamma to l, it's 1, 1, 1. Let me give you the coordinate points also. Gamma is 0, 0, 0. X is 0, 2 pi by a, 0, and L is, here it is k, denoted as k. It is pi by a, and pi by a. Okay. So what will be the distance between gamma to x and gamma to l, and the angle between these two vectors, 1, 0, 0 and 1, 1, 1. And has written something. I'm not sure which group you are referring. Let me show you the questions again. Okay. So anybody got the answer? So the coordinates are given here, gamma and x. So it is like calculating the distance between 2 points, right?
Option A.
Option A. Okay, let me calculate it also. I will also be sure that way. Okay. From gamma to so this is 0 2 pi by a square, so it is 2 pi by a. Okay, so yeah, the it will be in between a or c. Okay, then gamma to l, so it will be root 3 pi by a. Okay. Okay. Well, the answer is A, but let me calculate this also. So that will be angle will be dot product of these two vectors divided by, let's say it is A and this is B, so it will be A dot B by modulus of A dot B, A and B. So this is 1 by, so actually it is cos inverse, sorry. So the final answer will be, we did this for in the last session also, so it is answer will be 54.7. Okay, so the correct answer is option A. So I hope there is no doubt. Okay.
Ma'am, I have a doubt regarding this question. Can you please ask?
Okay.
Ma'am, what is the reference of nomenclature of these points like K, gamma, lambda, sigma? Uh, like now let us consider right now we are having reciprocal lattice for FCC direct lattice.
Hmm.
In case of any other lattice, we are forming the reciprocal lattice, and then how will we decide the nomenclature of those points? So will that be same?
So see, if you are asking about the kx, ky, and kz, so these are like x, y, z axes, right? So these axes are not constant. We take x, y, z as like this, but we can take any three perpendicular axes, right? Not necessarily this. Okay,
Yeah.
generally z we take it here, but it's the three perpendicular axes. So these are also like that, these are not unique. And gamma points, so when we, so reciprocal lattice we generally use to make the band structure, right? So these points are why we are considering only these points like gamma, l, and x or k. Okay, we consider these points because there are certain symmetry around these points. Okay, that is why, so when we discuss about band structure of a particular material, so these are the general notation, like 0 0 0 point we take as uh, gamma, and then along this direction this taken as gamma to x. So these nomenclatures are used these values like gamma, k or l, or the distance between gamma to l or distance between gamma to x. So these are like standard nomenclature. Those are used to make the band structure. So when we calculate band structure, we use this kind of nomenclature. But if you are asking the coordinates, so like x, y, z are not unique. You can take any uh, x's, any vectors in that case. So but your reference points should be one, and then based on that you can determine the other values like other vectors, how you will represent those vectors. Okay, so in this course the reciprocal lattice is considered mainly. Seems like these are only mathematical terms, but for practical applications these are used to calculate the band structure of any material.
Like ma'am, the L is being present in the center of the hexagonal. So can we take K point as L, and can we interchange these nomenclature
You
in this lattice?
So you can interchange in the sense this reciprocal lattice is repeated in all directions, right? Because it is a 3D lattice. But in general, the origin we take as 0 0 0. So in a coordinate system also, instead of this origin you can take another origin, but origin you take as 0 0 0, right? That is the reference point.
Yes, ma'am.
Yes, so if you are writing, suppose if you are writing something, you are drawing something, a band structure, say for silicon. If you write from gamma to x direction, suppose some band structure will be, it goes like this. So people will understand what gamma is, what x implies. So because of that, it is used. It's like a convention.
Um,
Okay. Okay, so answer is here A, it's not D. Let me correct it. So now let's go to the second question. Fifth question. So this question is on doping. I hope you will be able to answer this. In silicon crystal, it is doped with 10 to the power 15 arsenic atoms per centimeter cube. What is the equilibrium hole concentration at 300 Kelvin? Assume intrinsic concentration in silicon is 1.5 into 10 to the power 10 per centimeter cube. So we can try that. Okay. So what formula you will use here?
NP equal to N square.
Np equal to Ni square. So that is known as mass section law, right? So you can use it and tell me the answer. So arsenic is what kind of impurity or what kind of dopant in silicon? So arsenic is pentavalent element, right? So it will act as a donor in silicon. So this doping concentration is the doping concentration.
C, ma'am.
Yeah, yes, it is C. So I will also go through the steps here. And D is given as 10 to the power 15 per centimeter cube. Okay, and Ni again is temperature dependent. The question is given at 300 Kelvin. So at 300 Kelvin it is 1.5 into 10 to the power 10 per centimeter cube. Okay, so using mass section law, okay, so in 300 Kelvin, most of the dopant atoms will be ionized. Okay, so we can consider electron concentration is approximately equal to 10 to the power 15 per centimeter cube. Okay, so P will be it'll directly write 2.25 to 10 to the power 20 divided by 10 to the power 15. So it is to 10 to the power 5 per centimeter cube. So the answer is C. Okay, this kind of questions you have already solved. Yes. Answer is okay. Let's go to the next question. This is again on doping. A bar of gallium arsenide. So the material is gallium arsenide. It is doped with silicon such that silicon atoms occupy gallium and arsenic sites. So which one of the following statement is true? Silicon atoms act as p-type dopants in arsenic sites and n-type dopant in gallium sites, or silicon atoms act as n-type dopant in arsenic site and p-type dopant in gallium site. Silicon atoms act as p-type dopants in arsenic as well as gallium sites, and n-type dopant in arsenic as well as gallium sites. So what will be the correct answer? This is the crystal structure for gallium arsenide. So here again it is FCC structure with gallium atoms, these blue ones, and these are arsenic atoms. So what do you think? What will be the answer?
Option E.
What is the option?
A.
A. Yeah. So gallium is group 3, right? So the electronic configuration here is argon 3d10 4s2 4p1, and arsenic is group 5, argon 3d10 4s2 4p3. Okay, and we know that silicon has 4 valence electron at the outermost set. Here it is 3 and here it is 5. So if So you can think of it like this way: 3, then group 4, and then 5. Gallium, now this is silicon, and arsenic. Okay. So in silicon, when we dope with trivalent, it gives us p-type, and when we dope with uh, pentavalent, that gives us n-type doping. So if the number of electron is less, so that gives us p-type doping. So in this case, when silicon atoms replace arsenic, so gallium and silicon, so that will give, because number of electrons is less, there will be it will be p-type dopant. And when silicon replaces gallium, so silicon and arsenic, so it will be like doping with one extra electron, so that will act like n-type doping in gallium sites. Okay, so I hope it is clear. So the correct answer is A. Okay, let's go to the next question again. I hope you will be able to solve this question. So in a silicon crystal, it is doped with 10 to the power 15 donor atoms. Assume that intrinsic area concentration in silicon is 1.5 into 10 to the power 10 per centimeter cube. If the sample is additionally doped with 5 into 10 to the power 17 centimeter cube acceptor atoms, okay, so this I have written 2 times. Okay, what is the equilibrium electron concentration at 300 Kelvin? So you can solve this one. This is a problem on compensated semiconductor. So you can tell me the answer. Again, using the similar equations that you have used the second last question. Okay. Here Nd is 10 to the power 15 atoms per centimeter cube. This one. And Na acceptor is 5 into 10 to the power 17 per centimeter cube. And Ni has given at 300 Kelvin is 1.5 into 10 to the power 10 per centimeter cube. Okay, that is N.
Four 50, ma'am.
450. Okay. So, what type of material it is, whether it is n-type or p-type, it is compensated, but where the Fermi level will lie in this case, because electron concentration is 450 per centimeter cube. So here hole concentration is more compared to electron concentration, right? So the Fermi level will lie be somewhere here. Don't know the exact value, because overall it behaves like a p-type. Okay, so how we get the answer here? Donor concentration Nd is given as 10 to the power 15 and Na as 5 into 10 to the power 17. Okay, so Na is very greater than Nd. So why we are saying that it is very greater than? So you can compare the orders here. So you can see this is two orders. So if Na and Nd values are different by two orders or more, then you can directly consider that this condition, this kind of condition, and then you can say that so the whole concentration will be approximately equal to Na. Actually Na minus those ionized atom. Okay, but since it is at 300 Kelvin, most of the acceptor atoms will be ionized, so this is equal to Na, which is 5 into 10 to the power 17. Now using what is it, because it is written as equilibrium electron concentration, right? So in equilibrium, again using you can use this relation N into P equal to Ni square. So we can calculate N, which will be 450 per centimeter cube in this case. Okay, so here we are taking few assumptions, right? That Na is very greater than Nd, so P is approximately equal to Na minus, which is equal to Na at room temperature. So that's why we are getting P as equal to Na, and then we are using, because this is in equilibrium, the system is in equilibrium, so we are using this formula, and then we are calculating as N. Okay, can someone tell me where these assumptions will break down, like where we cannot solve this question directly using these steps? Okay, give me a minute. I hope there are people in this meeting. Okay, yeah. So if here we cannot use this formula when Na is not very greater than Nd, right? In that case we have to use different formula. We have to calculate what are Na and Nd, and also here we are considering 100% ionization, so Na minus is equal to Na. So that may not be the case if it is not at 300 Kelvin. Say if the temperature is very low, then not all the accepted atoms may be ionized. So in that case also we cannot use this formula. Okay, again if there are any extra electrons and hole pairs due to some external excitation, then also we cannot use these formula. So you have to be careful while solving this kind of problem. What are the conditions given? So what are the assumptions you are making? Okay. Okay, so let's go to the next question. Okay, here the answer is A. I hope everyone got the answer and the concept behind it also. Okay, again here I have already given the answer. Let's go through this question again. What is Brillouin zone? A region of energy space that encompasses all the unique values of energy. A region of position space where the electron is allowed to reside, a region of K space that contains all the unique solutions of the wave equation, or another name for the unit cell of the crystal. So the answer I have already given is C, but what do you think about the other options? Okay. So someone is saying something.
What is meant by unique solutions of all the wave equation? I can't understand. I can't get that.
So how we get the possible energy values for electrons, that is by solving what this wave equation is, Schrodinger's wave equation, right? So using Schrodinger's wave equation, uh, what are the solutions of the wave equation, and those, so that will give the possible energy values, the solutions of the wave equation. So Brillouin zone contains the possible energy values in that K space. So K space is, let's consider a one dimensional K space, so that will be easier. Let's consider only Kx. Okay, so there will be, suppose the Ek relation is like this. This is in energy scale. So the solutions of the wave equation will give some energy values, which are these energy values for some K, right? And here you can see there is no energy value in this region. That means there are no solution of the wave equation in this. In these energies are not allowed according to Schrodinger's wave equation. Only these energies are allowed. Okay, so Brillouin zone actually represents those, the energy states which are allowed for electrons and which are not allowed. So these are forbidden. Okay. It's, let me remove this. So you got my point, right? These are
Yes.
okay. Basically, so this wave equation here means Schrodinger's equation, and for electrons, the properties of electrons, those are described by Schrodinger's wave equation, and based on that we get information about the electron, like the energies and what is the momentum. So K is related to momentum, right? This is E if it is K, if it is E, and this is K. So momentum is P equal to H bar K. So P is momentum, H bar is reduced Planck's constant, so this is a constant, and so that is why K is related to momentum. So K space, uh, sometimes it can be referred as momentum space also in terms of P. Okay, so in terms of P, so in momentum space also the allowed energy levels can be explained. Okay. Okay, so the answer is C. So next, let's go to the next question. In EK diagram, select all that are true Each portion of the curve represent allowed band of energies. The curves have zero slopes at the top and bottom. The curves are parabolic near the top of the valence band. The curves are parabolic near the bottom of the conduction band. So I have just given you the EK relation in one dimension. So you can tell me the answer. What will be the answer for this question?
Then I think the
D.
nature of the course is parabolic in both conditions.
See what is given here. Select all that are true. Right? There may be more than one correct answer. So tell me first, then I will explain.
Then I think it is parabolic in both of the conditions.
Okay. So you're saying C and D are correct, right? And what about the other options, A and B? See, okay. So again, I will explain in terms of 1D system, right? It is difficult to draw a EK diagram in 2D or 3D. So this is K and this is E, and typically this is the conduction band kind of, and valence band will also have this kind of, so there will be bands above this and below, there will be below this, but for us the we will mainly concentrate on valence band and conduction band because these are most interesting for us, okay, for conduction. So there will be electrons in the conduction band if there is current flow, and there will be holes. If there are holes, then there will be current flow in the because of this holes in the valence band. So let's consider this EK diagram. Okay, so here so these are the x's, right? So these portion, so all this, each point in this diagram, those will represent allowed energies for electrons, right? And in this region, so since there is no energy, uh, so no momentum, corresponding momentum value, so these energies are not allowed, okay. And then again, these energies are also allowed for electrons can occupy these energies. So if an electron has is in at the top part of the valence band, say, and if it gains energy, then it can go to here, not here or not here, because there are no no energy states. So the first option is also correct. Each portion of the curve represents allowed band of energies, okay, each portion, and there are many states between these two also, right? And then the curves have zero slope at the top and bottom. Okay, let's first consider these two, right? C and D. The curves are parabolic near top of the valence band and near bottom of the conduction band. So from this figure also you can see that it is, we can fit a parabola at the bottom part. Okay, the parabola will not fit nicely at this part, at this edges. Again we can fit a parabola here also. This will fit nicely at the top of the valence band, at the bottom of the conduction band, but at the edges the fitting is not nice. So the curves are parabolic near the top of the valence band and the bottom of the conduction band. Okay, so these two are true. So this will be the ek relation will be like E, some energy value which is, let's say, EC, edge of the conduction band, plus some constant n k square, because it is parabolic, right? Okay, so you can see here the slope, the curve has zero slope. That means, so this is constant, right? If you take the derivative of E, like dE by dk, I mean, what I am saying that the slope will change here, then the slope will be constant at this top part, and then the slope will again change. So this slope is there will be like no slope also, like it is a constant slope. Okay, so this will be like a constant at this point locally. So this is also true, so the answer will be this 4. Okay,
But the slope is not zero at the top. Right?
okay, slope is not so yeah, slope is constant at the top, right? So what will be in form of some constant? Constant and x square. Okay, h square x square. Okay, so I will check this. Yeah, the slope is not 0, but the slope is gradually changing, and then locally at this point it is constant. So maybe this is not correct, but these three are correct. Okay, I will change this in the final PPT.
No, I am having one question.
Okay,
We are, yeah, we are taking the electrons' energy levels at discrete level, right?
electrons energy levels are discrete level, but there are so many energy levels, so the gap is very small, so that is why it seems like a continuous band. So
Okay,
these are discrete, but these are the distance between these two states are very small, so that's why I'm drawing it like a like continuous line.
yeah, okay.
Okay, okay. So this is the next question. This is related to effective mass. So the energy dispersion for electrons in one-dimensional lattice with lattice parameter is A is given by E naught minus zero point 0.5 W cos Ka, where W and E naught are constants. So the effective mass of the electron near the bottom of the band is, so what is the answer? You can try first and then I will tell you the answer. So this is a one-dimensional crystal, one-dimensional lattice. The question is clearly visible, like I will increase the font size if you want.
Yes, clearly visible.
Okay. Can you solve the question or I should give some hint? One minute, okay.
Now, from the expression, the effective mass will be h cut square divided by d2 e over dk square. Is it correct expression?
Uh, Tell again, I couldn't hear.
Effective mass equals h cut square divided by d2 e over dk square.
Yes, okay, that is the expression.
From that expression, we will get the value h cut square divided by omega e square cos ka.
So see, the question is effective mass of electron near the bottom of the band. Okay, so you should also think about what will be the value at the bottom of the band. Now maybe we'll be able to give the answer in terms of as given in this options, right? Okay, so let me tell you uh, the concept how we get the expression for effective mass as h bar square del 2e by del k2. Okay, so as we have discussed in the last question, in EK relation, the bottom part here, bottom part of the valence band and the top part of bottom part of the conduction band and top part of the valence band, we can use parabolic approximation, right? We can fit a parabola here. And for free electrons, so for free electrons, the EK relation is E equal to h bar square k square by twice m. Okay, h bar is reduced plus Planck's constant, k is the wave vector, and m is the mass of electron. Okay, so for free electron it seems like it is half mv square, right? Similar to like that. So we use similar expression because we can fit a parabola here, so we use similar expression but with an effective mass, okay, for electrons in the crystal. So this is for one dimensional crystal. So here I am only considering k, so in 3D it will be kx, ky, kz. Similarly here this part will be kx square plus ky square plus kz square. So using effective concept of effective mass and parabolic approximation, what we write as EK relation for one dimensional electrons in one dimensional crystal as h bar square k square by 2 m star. So m is effective mass. So if you take first derivative here with respect to k, this is one dimensional, so I can directly write dE by dk, but let me write this way. That will be h bar square k by m star, and double derivative will be k2 h bar square by m star. So that's how we get the expression for effective mass, m star equal to h bar square del 2e by del k2. Okay, now remember this is true only here, not here. Maybe if the band goes like this. Okay, so now we get the expression for effective mass. So what is given? EK relation is given like this. Okay, go to the next slide. Okay, so for this case, dE by dk will be minus, then again it will be plus, so okay, 0.5 WA sin Ka, right? Okay, and double derivative will be half WA square cos Ka. So m star when at the bottom of the band, that means where k tends to 0, right? this is K. uh, if this is the bottom of the band, then K tends to 0, so we can write this as 0, K as 0, so the expression will be h bar square, 2 will go there, and W A square. Okay, so the answer is A. Okay. So this is the effective mass for the given EK relation. Okay, I hope it is clear. Okay, is there any question? Okay, I hope there is no question. Okay. And someone turn on his mic, so if there is any question. Or should I share the screen again? Should I show the answer again?
No, ma'am, no questions.
Okay, no question. Okay, for this session I have these 10 questions. So since we have time, let me ask you a question. So we have already solved questions on reciprocal lattice. So I'm giving you an 1D lattice. Okay. So the lattice will be like this, only in one dimensional. And this distance is A. Now tell me the direct lattice vectors.
No, screen is it's not shared.
Oh, okay, okay. Thank you. Okay, now it is visible, right?
Yes, ma'am.
Yeah.
So what the direct lattice vectors and reciprocal lattice vectors. So it is a 1D lattice. So what will be these? So we have done for FCC. So what will be these lattice? So I have mentioned, right, you can take the similar approach to get the direct lattice vectors, reciprocal lattice vectors for any kind of lattice. So you can try this, because nowadays there are 1D systems and 2D systems, 2D material and 1D material, so this might be relevant. You can try this. Okay, I'm giving you a couple of minutes. Okay. Are you guys trying, or should I give you the answer? I will show you the steps. Okay. Okay. So for directly, let us first start. So we will define three vectors, even though it is in one dimensional, because in the expression for reciprocal lattice we have to divide it by volume. So here a1 is a x cap. Say this 1D lattice is only in the x direction. Then a2, this will be there is no distance, we are only defining y cap, only the direction. Okay. And a3 is z cap. So okay, there is
Uh,
so
if it is 1D means how can we take V cap and Z cap? It
no,
will be zero. Right?
so these are like, this does not have any value, only the direction. So we are only taking direction, because so for reciprocal lattice we will divide it using, so 1 a cross 3 divided by v, right? So for calculation of volume we are just taking this, these are just mathematical expressions. So finally, even in reciprocal lattice, for 1D lattice, so the reciprocal lattice should also be 1D. So you go through the steps with me, so we'll see that finally in the reciprocal lattice b1 b2 b3 also only one will have this term, inverse of the length dot term. Okay, so these are just for the mathematical calculation I'm taking. Okay, but there is no value associated with it is only a in this direction. Okay, so in
What will if there is no space to move? How can we define that space? Maybe it's like defining a fourth dimension in a real life, right?
yeah, it is defining, but mathematically we can define, right?
Yeah.
Mathematically we can define n dimension also. So I'm just taking this. So even without going through this exercise, you can see that this will be in terms of 2 pi by a something, not x cap, k x cap, right? So
Yeah.
why I am showing you this step, so that you can get the final, like if any kind of lattice is given, so you can also do like it is for 2D also, you can do these steps and finally get the answer.
Yeah.
Okay, so for 1D lattice, if it is in length a, so that is in nanometer or whatever the dimension is given, so finally the reciprocal lattice should be inverse of that. So kx is inverse of that, right? So finally the unit you can see from this here, 2 pi doesn't have any unit, and a is has the unit of length, so the final unit is 1 by length. Okay, right. So for reciprocal lattice, so b1 will be 2 pi by a x cap, b2 will be, you can calculate, so here I 2 pi by a, okay, 2 pi y cap. So here you can see there is no unit for this, whereas this has a unit of length. Okay, you can calculate a1 dot a2 cross a3, right? This is A2 cross A3, and this will be A. So even though this is the expression for volume for parallelepiped, but you are getting the answer is A. So the unit is of length. Okay, I think it is clear, right?
Yes.
Okay, you can try for 2D systems also. If it is a two-dimensional system, two-dimensional lattice, say square lattice A and A. Okay, because the 3D structures, those are very difficult to do in pen and paper. Like in here I have given the Brillouin zone for FCC lattice. So this structure is very complex already. So in 1D and 2D you can calculate and check, like you can also determine the gamma to x points, those points, and then you can calculate what are the values. Okay. Okay. Is there any more question, any doubt?
Ma'am, can we get the sums of first week lecture?
So you are saying the solutions?
Yeah, I mean problem solving session. I
Problem solving session, yes. So the recording will be there. It will be shared by the NPTEL team. So that we will get notification. Okay. So I'm not sure when the notification will be given, but I've already done the recording. I'm also doing the recording for this session also. So we will get that, but that will be
The
initiated
recording
from
of the last, ma'am, the recording of last session is already available.
last session. I have uploaded, but the notification, the links and everything, that I don't know like when those will be shared, but I have already shared from my side, so you will get it, it will be notified to you. Okay.
Ma'am, that is available on the website of NPTEL.
Oh, that is available in the website. Okay, okay. I have uploaded already, so maybe they have already shared the link. Okay. So like after finishing the session I try to upload it. Okay. And there are other TAs also, so they are also taking other live sessions, so they will also share. So the timing I am not sure exactly. Okay. Okay, so in the last class few of you told me that you work on 2D materials, right? For example, here the EK relation, we have taken the double derivative. So if the EK relation is linear, say for graphene, right? So in that case, can we use the parabolic approximation? Suppose the EK relation is like this. We cannot fit a parabola here, right? And if we try to take this equation, the effective mass will be so basically we cannot use the effective mass, the parabolic approximation in all kind of EK. Okay, that is what I wanted to say. So in some material, for example in graphene, the EK relation is linear, so we cannot use the parabolic approximation and use this kind of formula. So it depends on the band structure. So that is what I wanted to say. So is there other questions? I'm sorry if there are background noises. Okay. Okay, someone mentioned the videos are available in NPTEL website. I'm also not sure exactly. Can you please tell again? So whoever said that. Uh,
Vikram, can you fetch the link of the last session and I will upload in the comment box.
okay, so your voice was not clear exactly. So okay, it is available. Okay, so you can use that link. Okay, whoever asked this question, and PPT also I will share, and NPTEL team will share with the students. Okay, I'm sorry for the background noise. Okay, so I upload all the PPTs after the session, and okay, so yeah, in the drive I will upload. As soon as I finish the session, then I upload there. Okay, I'll upload the PPTs. Okay, so generally I prepare the PPTs earlier, so I will share those that PPT. So here I'm not sure, some of the writings may not be clearly visible, so I will share, but the questions are same and the answers are also same. So I'll share those PPTs. Okay. Yeah. Uh, so you have submitted the assignment 1 already? Assignment 1 and 2, I guess. I have not. Okay, check the deadline for the assignment also, and I think it is due in this week. On 7th, the one assignment was due. Okay, let me check. Okay, first assignment is due on 7th. So it is mainly on crystal structure and planes, so that those were discussed in the last week, and then assignment 2 is due on, let me check. Okay, due date for both assignments are same. Okay, you should check. I think it is 7th for both the assignments. Okay, and there are questions on dopings that we covered in today's session, and then reciprocal letters. These topics were covered in this week. XRD, okay, and then EK relation. Okay, check the okay, both on 7th, yeah. Okay, check the due dates and submit accordingly. Okay. Okay. I think it's already 5 o'clock. We can stop the session. Okay, and we will meet in the next week. Thank you, everyone. I hope the session was useful.
Thank you, ma'am.
Okay, and if you have some doubt related to this particular sessions, you can mention the session and then submit in the discussion forum also. Thank you.
Thank you.